Of all the introductions I've ever gotten in my life, that is by far the most recent. Okay, so my talk is called, oh, how to change the slides, by the way? Oh, I forgot the controller. Okay, so my talk is called How to Build Mainnet Ethereum Clients. Don't tell the guy from Coinbase because I'm not trying to get sued. How to operate this device. Okay, cool. So this is my agenda. You heard a little bit about it from Dan, but just going to talk a bit about the challenges that we faced implementing this client, the methodology that we followed, some architecture, and then where we're going to take this project going forward. Okay, so the reason why I got interested in Ethereum initially was because I found this concept of a world computer to be pretty cool. There's a lot of developers that are working on Ethereum and a lot of interesting projects. And so this has created this sprawling, sometimes adversarial peer-to-peer network. And so, yeah, this was our starting conditions for creating this piece of software. And so, yeah, what is an Ethereum client though? So essentially what an Ethereum client is a server and an application all rolled into one, which is pretty cool. And right. So according to this book, Mastering Ethereum, which Andreas Antonopoulos has just released, you can know that, yeah, building an Ethereum client is easy because it's defined according to a formal specification. Okay, but so I should preface this with, I have nothing but the utmost respect for Dr. Gavin Wood. I think he's one of the greatest hackers of our generation. But nevertheless, there are some serious problems with the yellow paper if you're trying to use this as the basis by which you're going to implement an Ethereum client. And so, not the least of which are the fact that some of it is out of date, in addition to the fact that it's very dense and hard to comprehend. There's parts of it that are, you could say, typos or just factually inaccurate that one of my colleagues took great delight in sussing out. And yeah, it's also incomplete, so it doesn't talk anything about the networking. Okay, so another challenge that you might face as a implementer of an Ethereum client is that a lot of the concepts that you have to be familiar with are highly non-standard for general computer science, such as Merkle-Patricia tries or trees, or however you say this. So don't even know how to say it, let alone how to build it. And then RLP, so this recursive length prefix encoding, is also pretty difficult. There's few resources about that. And the resources that do exist are very sparse. And so they're often contradictory resources, some of which are outdated. And they're not all collected in one place. You have to find them out from all over the web. Yeah, in addition to the fact that there are such nuances in Ethereum clients as consensus bugs. So some misimplemented protocol components, which have since become canonical. And so clients that want to implement the Ethereum protocol and communicate as a well-behaved responsive peer on the network have to implement these mistakes, basically. And let alone those mistakes, there's also just the fact that these milestones are occurring every so often, and you have to stay on top of them, or your client will become out of date very quickly. Okay, so key takeaway from this section is that building a mainnet compatible Ethereum client is hard work. All right, so I like this quote and this idea that life is like learning to play the violin in front of a bunch of people, like, you know, trying to perform a violin solo and learning the violin as you're playing it in front of everybody. And this is kind of what we did when we were building this client and trying to learn the specification as we were going. But fortunately for us in 2018, this is called agile methodology, so we're on trend. Okay, so one of the specific methodologies that we followed, because we were trying to implement it without looking at any of the existing clients because of licensing issues and so on. We use test-driven development. So the Ethereum Foundation has a whole suite of reference tests that they make available. So we could implement components and then test them against those and make sure that it behaved correctly. So in addition to this, yeah, we would try to follow a strategy of building out components such as when we wanted to build the transaction pool, for instance, we built the transaction pool and then tested it through JSON RPC with the send raw transaction message. So building out an underlying component and then a test surface for that component concurrently. All right, so another important element of our methodology was we were under kind of time pressure. We started it around September 1st, 2017, and gave ourselves the rough deadline of September 1st, 2018, before DevCon 4, as when we wanted to release by. So we made that deadline, but yeah, a lot of crunching was involved. One component of our team that is important is that we're totally geo-distributed. So we're based all around the world. And some lessons learned from this is that you should try to cluster people in hubs of activity. So initially we had people in California, people in New York, in Berlin, in Australia, and some of whom were working on the same team, but they had very little overlap in work hours. And so miscommunications were more likely to occur under these conditions. So we built this client in Java, and I know that many people, myself included, when they first hear Java, they say, oh, this is kind of boring language, not sexy, because I learned about it in school. But actually, I have come to really like Java since working on this client. And I've also come to learn and understand that when you're writing some very small file to do some small task on your computer, maybe it matters if you write it in Haskell or if you write it in Java, and the Haskell one will be incrementally faster. But when you're building a 1,000-line software system that has many interacting components, the architecture that you choose is much more important than the language. So all you Haskell developers can have fun writing Haskell on whiteboards. Okay, so this is a diagram that we made that roughly describes the Ethereum architecture as implemented in the Pantheon client. And so, of course, every diagram like this is a big oversimplification, and there are many ways to create such diagram. And yeah, so we had many ideas for my friends and colleagues on how to best articulate it. But what you can see here is that the peer-to-peer networking component is to the side, since it's meant to convey that you're interacting with co-equal peers across the network. And then we put the storage on the bottom because this is what's being persisted to disk. We put JSON RPC on top because this was the interface that we're exposing to the world. So we have core there in yellow, which is the active processes that are driving the network forward. And then we have block processing, which is validating that all the information that you're getting is in line with the specification. Okay, so we can talk first a little bit about the peer-to-peer, about the dev-P2P implementation that we used, or that we implemented. So you can see there on the side of the diagram that we have all of these executors, which are something that is, according to my understanding, unique to Java. So we have thread pools for all of these. And this was in order to make it such that we wouldn't have to block on those network ports as we received messages from our peers. We could spin off sub-processes and then have those executing for receiving blocks, for receiving transactions, etc. And so those are all defined by this eth subprotocol eth messages that you can see there on the bottom. So I also just put a reference to this recursive refresh, which was just some component of this that I was working on recently, defined by the Kademlia algorithm. So kind of a neat thing, but I guess we can press on to the other elements of the system. All right, so in this core, it has basically three main responsibilities. So at this moment, people don't really use Pantheon for mining, but we nevertheless have this functionality, which is why it was the smallest one there. Basically, it's more of minting blocks. And so the main things that it does, though, is the Synchronizer and the block propagation manager. So these both have two different components, which we can talk about in more detail. Okay, so Synchronizer has this downloader and block propagation manager. You can think of Synchronizer as the heart of the machine because it's ensuring that the data that you receive from the network is consistent with the data that you're persisting to disk. And so there's two states that you could be in when you're running a client. One of which is that you're behind and you're trying to catch up to the rest of the network, so you're downloading blocks from your peers. And then the other is when you're caught up to the chain head, and then you want to propagate blocks. And so those are described by those two boxes. And so these are the different components of the downloader operation. Let me just take a peek because I kind of forgot what I wrote on there. Okay, yeah, so basically it has these different tasks which correspond to where you're at in the process. So one of which I wrote some text about, is the determine common ancestor task. So when you receive some message from one of your peers, you want to determine where you have a common history with that peer. And so we implemented it as some kind of modified binary search algorithm, which is one of the reasons why I like working on this team and working on Ethereum clients, is because you have a lot of opportunities to implement cool concepts and neat little algorithms like that. All right, what does this one say? Somebody say what that says? I don't have my glasses on. Ending blocks. Oh, right. Okay, so yeah, this is from the block propagation manager. So imagine that you're like caught up to the chain head, and then you receive some block to which you don't have the parent. You'll have to cache this block so that when you do receive the parent to this block, you can incorporate it into your representation of the Ethereum blockchain. This, as I recall, is the validator, right? Yeah, okay. So yeah, I mean, pretty self-spoken, just validating that the data is consistent according to the Ethereum specification, which you want to persist. And yeah, okay, so this is our state representation. And so it has four components. One is relating to consensus. So ETH-hash, the mainnet Ethereum algorithm, doesn't have any meaningful stateful component, but we have it in there because our client also has IBFT and clique consensus, which are alternative consensus algorithms, which do have states. Yeah, sync state is just statistics about where you're at in the syncing process. Oh, yeah, world state is related to accounts. So that's code hash, date, root, balance, and nonce. And then blockchain is, so it's all the blocks, right? And a block is an association between a block body and a block header, etc. It also has some extra information about chain head and just some nice helper functions. So this, as I was saying, we had some discussions about how best to represent this client as a document, or like a UML document. And so this is an alternative. I put the little heart emoji there because the synchronizer, as I was saying, is really the heart of the machine in my mind. And then, so we had here the JSON RPC on the one side, because this is the interface to users, to dApp developers. And then we had the CLI, the logging, and the metrics on the other side, because this is the interface to operators. So yeah. Then on this one, also we put the dev P2P on the bottom, because in one sense, you can think of this as what's underlying the running of the clients and the storage on the top. But so, and then in addition, yeah, these components are not so cleanly separated as here. This is kind of idealistic. All right, so can get now into the evolution of the Pantheon client. So I like the concept that startups are hard, but stay-ups are harder. And there is currently an elephant graveyard of Ethereum clients that exist because based on all the challenges that I was talking about before, it's hard to build an Ethereum client, but it's harder to build it and then maintain it. So right now there exists basically only Geth, or as some people call it, Goethe, at Parity, and now Pantheon. And so yeah, we're intending to keep it going, and then these things I'm about to describe, yeah, are like how we plan to do that. So the Ethereum Enterprise Alliance was something that was always in our mind as we were building this out. And we're intending to have our client be fully compatible with the forthcoming Enterprise Ethereum Alliance specification. So we have a standards team that's also part of PegaSys, which is the protocol engineering group of consensus. And yeah, so that should be released soon. We're planning for a February release of this enterprise version of Pantheon. And so another thing that we're always thinking about is ETH 2.0 or Serenity, and then how we can harden our Pantheon client for this and incorporate it into these coming changes to the Ethereum protocol and the Ethereum network. And so one way that we've been doing that most recently is through the idea of beacon chain. So in our R&D section of PegaSys, we've spun up a team to implement this beacon chain concept, and they're working with us Pantheon core developers to see which components are reusable and how we can meld the two of these concepts. And yeah, so if you think that this is interesting, if this Pantheon is something that you'd like to learn more about, then allez, viens. We invite you to this Getting Started with Pantheon webinar that we're going to host on the 18th, or it's an open source project. You can find it on GitHub. I'm happy to talk to anybody who has interest in that. And yeah, I'd be happy to answer any questions that I might have inspired in any of you lovely audience members. Thank you.
Right, so you said that you built this client with enterprise in mind. What kind of out-of-the-box features does Pantheon support that would enterprises would find useful?
So two things that we support currently, which we thought of as enterprise-minded features, were the Clique and IBFT. We're also right now in the process of instrumenting the client with many metrics because it's our intention to have it be one of the best performing clients. So we wanted to accurately measure this. And so those are going to become part of the code base though. So they'll be available to people who are operating nodes, et cetera.
To view real-time calls that are happening on the network, have you guys considered implementing in your logging area or output something easier for developers or security researchers who want to see what's happening real time?
Yeah, everybody kept saying this, but can't you just do that EVM call? It's like a command line option on Parity and Geth, isn't it? Or, I mean, it'd be pretty easy just to, so it's an open source project. You can just go and just have it spit out all the opcodes that are into the EVM. I think it'd be pretty easy. I mean, I don't think we have a plan to make that a feature. Yeah, but I think it'd be easy to do. Yeah, okay. Any other questions? Yep.
Does Pantheon support all the same JSON RPC that Geth and Parity do, or?
Yes, it does, and more.
Like what?
I mean, I don't know. Like, yeah. So all of the JSON RPC interfaces are like a little bit different between clients, but we implemented all the ones that they do, and we're trying to implement some additional ones. I'm not sure exactly what. Oh, I know exactly what. Okay, so my friend Zach Mitten, shout out to Zach Mitten, is working on some new JSON RPC call where you could have proof, so that you would get some callback, and then you'd have like the hash proving that it was from some block or anything like that. He was explaining it to me, and I was only half listening. But yeah, I'm not a dApp developer myself, so I don't really know all about this kind of stuff.
We're done.
Okay, cool. Thank you guys.